The next trend we have to talk about is ionic radius. So our cations, they're positive. Remember, cats have paws. Positive ions are usually your metals. They have lost an electron. Cations are always smaller than the original atom because what happens when they lose or an electron or a couple electrons is the entire outer energy level is removed during that ionization process. So like if you remember, if you look in group 1A, they have one valence electron. So they only have one in their outermost energy level. When they give up that electron to something else, they become the positive one charge. They've lost that whole entire outer energy level. So their furthest out electrons in their valence shells are usually the ones they're going to give away. And those furthest out electrons in the valence shells, once those are gone, it makes the atom smaller overall because it doesn't have any electrons further out in that further out energy level. On the contrary, your anions, your negative ions, your nonmetals, remember they gain electrons. They're always larger than the original atom because what happens is the electrons are added to the outer energy level during ionization. So they're gaining electrons, so they're getting bigger. So the ionic radius makes sense because in your cations, they're getting smaller because they're losing electrons. Your anions, the ones that are gaining electrons, they're getting bigger. We have electronegativity. Elements with high electronegativities, especially our halogens, are group 17 right before their noble gases. They're sort of like homewreckers of the periodic table. They really want to steal those electrons from some other element, and they'll move heaven and earth to get it. So electronegativity is a measure of an atom's attraction for another atom's electrons. So it's an arbitrary scale that ranges from 0 to 4. The units are Paulines. So remember, you do want to remember all the units of these. They are on your mini periodic table. Generally, the metals are electron givers. So metals will give up their electrons, so they don't really want to take anybody's electrons. They're already trying to get rid of the ones they have. So they have very low electronegativities. Nonmetals are electron takers, and they have high electronegativities because they're doing whatever they can to get those extra electrons to get their full outer shell. Our metals on the far left of the periodic table, they're wanting to get rid of theirs. So they don't really want anybody else's electrons because they're still trying to get rid of theirs to get down to a full outer shell. So your electronegativities depend on if it's a metal or non-metal and where it is. So if we look at the trend for electronegativity, our noble gases have like 0. They don't even take effect because they're pretty much stable, don't want anybody's electrons, don't want to get rid of electrons. So they have noble gases have 0 Paulines for their electronegativity. Remember, Paulines is the unit that we use to measure it. An exception to that is we have krypton and xenon. They have a slight property, so they kind of want to take electrons sometimes. They're kind of reactive sometimes. But overall, noble gases are stable. They have their full set of 8 valence electrons, so they have 0 Paulines for electronegativity. Fluorine is the most electronegative element. Down a group as you go, electronegativity decreases, and from left to right across the period, electronegativity increases. So you can see here we have an increase of electronegativity as we go left to right, and a decrease as we go down the group. So really, the electronegativity is increasing. Fluorine is the most electronegative. It is going to do anything. It is so reactive, it'll react with anything to try to get its extra electron and be happy at a full outer shell. So you can see our electronegativity trend. The higher up they are here, and their colors tell you their electronegativity. Then we have electron affinity. Affinity really just means to like love or be attracted to something. So elements that love electrons and will go through anything to gain electrons, thus they have a high electronegativity, also usually have a high electron affinity. So the energy given off when an atom gains an extra electron is just what electron affinity means. This trend is very similar to electronegativity. So pretty much just think of it like electronegativity. It still has to do with the attraction for electrons. The more they want the electrons, the more times they're going to give off energy when they're gaining that extra electron. Our next trend is the melting and boiling point. It's highest in the middle of the period, so it's actually, they have low melting and boiling points on the outsides, and then as you get closer to our transition metals in the middle, the melting and boiling point is the highest. W, or tungsten, has the highest melting point of all the elements. So on this trend, you would even like circle tungsten and point out that it has the highest of all of them. If you fish, you might remember that tungsten's often used for weight. I'm not really sure if that's because it matches the high melting point, but it could possibly be, and that's a thing that definitely you should research if you're into that type of stuff and you like to fish and stuff. but tungsten has the highest melting point of all of the elements. It has to get really hot before it'll start melting. Then we have density and solubility. Remember, density is our broken heart equation, mass divided by volume. As you go down a group, the elements get more dense. So they weigh more for their size. If you had two marbles shaped the exact same size, one that's higher up in a group is going to feel lighter than one that's further down in that same group. Solubility is just how easily something dissolves. If you're making lemonade from mix, your sugar mixture would be the solute, which is the substance being dissolved, and then the solvent would be your water. So if you're making lemonade, your solute would be sugar, solvent would be water, the one doing your dissolving. As you go up the group, the elements are more likely to dissolve in a solvent, like water or other things, but solubility has the opposite trend of density. It increases as you go up a group. Density increases as you go down the group. Our last trend so far is metallic character. It's just a simple relative measure of how easily atoms lose or give up electrons. The more they want to give up their electrons, the more metallic character they have. It's pretty much a trend opposite of electronegativity. Electronegativity is how much they really, really want those electrons. So remember, fluorine has the highest. It's going to steal somebody's electronegativity. Metallic character is the opposite trend. How much they want to give up their electrons. So our arrows are literally going the opposite direction here. The highest metallic character are the ones that want to give up their electrons the most. They're the givers, the donators. They're the charity ones. They really want to just give their electrons away. So general overall reactivity, comparing those, it ties kind of all the previous trends together into one package. You can look at this picture. Our noble gases are blacked out because they're not reactive at all, except for krypton and xenon, if you remember just a little bit. The most reactive metals are the largest ones because they want to give away their electrons, so they give away their electrons a lot easier because they're larger. The most reactive nonmetals are actually your smaller ones because they take electrons a lot better. So you can see the most reactive metals are way down bottom left. Most reactive nonmetals way up top right, not counting your noble gases. So the overall reactivity just depends where they fit on these lines in those trends overall. So here's all of the trends put onto a periodic table so you can kind of compare them. You'll want to fill out a mini periodic table and color these in. Remember your melting and boiling point, they get the highest at tungsten. You might want to circle that one. You can see density goes down as you go a group, solubility is opposite, it increases as you go up. Here I have my ionization energy in the light purple, and then it increases as you go to the right. Atomic radius, they get bigger as you go down and to the left. My electronegativity, again, increases as I go up and increases as I go to the right. Fluorine has the highest electronegativity. Notice on this arrow, they didn't go all the way to the noble gases because the noble gases don't have any electronegativity. So this arrow, the green one, stops at fluorine. My other two are including those noble gases in theirs.